thank you for joining my talk. I've been working with Linaro for about 2 years. Previously, many companies, including ARM. And as you might imagine, working on the cloud, in the cloud space, is something that is relatively more recent for most people who are familiar with ARM. So I'd like to ask before I start, I've been given 25 minutes, but I tried to make it shorter. So just in case there are questions, and I'd like to ask if anybody is working, whether you're within Linaro or outside, if anyone is actually working on porting code from X86. Anyone? Okay. At least one person. So this is mostly related to porting code from X86 to AARCH64. And I personally have been working within the cloud context in the past 2 years, but it could apply to non-cloud targets. And you could look at the presentation as a guideline. So, for instance, if this is the first time you're working on a project and it's a quite complex project, which is often the case with projects we're involved with, you need some kind of roadmap. And I hope that this presentation will provide the roadmap for you guys. So first, a quick overview. I'll get into the details of what it is that we would like to measure when it comes to performance and porting code from, well, not necessarily x86, other platforms to ARM. And when we are measuring the what, speed, energy efficiency, and the quality of output are important. The last point is something that usually people don't think about unless you're working on some kind of machine learning or perhaps some visual applications. But it is very important, especially with machine learning applications. So 3 different types of metrics or classes of metrics. There are probably others, maybe I haven't thought of, but these are the main ones we normally deal with. Then I'll get into the steps. So once you know what kind of metrics you would like to measure and what is important for your particular project, these are the steps. So you could look at measuring your system's performance, and by system I mean things that are not necessarily within the source code within your application, but they usually often affect the performance and different aspects of your application. Then once you've done your measurements of everything in the system, including your code, it might be time for optimizing and fine-tuning your software. And I'll explain a little bit about the steps related to doing the optimization, or rather what we have decided would be good for our clients. And the last step is, of course, maintenance. So once you've got your code ported and optimized and you're deploying, obviously you would like to continue developing the software and the system and maintaining the different aspects of it. So it's your application, if you're running on Linux, for example, keeping up with the latest updates. And then the how. So I'll get into the how. You know what you're measuring. We'll talk about the steps, how to do that. And then finally, you want to know the how exactly, step by step, what is involved. That includes the easy stuff, so portable code, that's already kind of easy to port from one platform to another. Then we have the moderate stuff, vectorization, for instance. And then we have parts that are a bit more difficult or expensive. And it doesn't necessarily mean scaling the number of engineers involved with your project. It might be just the time needed. Some of these cases, what I call the more classified as more expensive, throwing more people at the project doesn't necessarily help. You really need to spend more time. And that's what makes it more difficult or expensive. So that is the overview, and I have a case study about the how, and then at the end I'll do a quick review of the tools that we are usually using for our projects. And the tools that I'm going to cover, they are kind of generic tools. They apply to all sorts of different ARM chips and ARM platforms. But of course, there are IP out there that different types of IPs where you find very vendor-specific tools. We're not covering those, but being Linaro and having worked on many different projects, as a team, we have experience with a lot of those other tools as well. What I'll cover is Linaro Forge and ARM Performance Studio, as well as the Perf, which is the beloved performance tool within the Linux community. So now let's get into the metrics. And I would like to have a little disclaimer. They are just guidelines. There are lots of details that I may have not covered here, and things are different from vendor to vendor, chip to chip, project to project. So take these as just a high-level overview of what you need to take into account for a project like this, porting code. Speed obviously is wall clock speed is one of those metrics. It's very important. Almost every and any tool you use out there, performance measurement tool, it involves some kind of CPU cycle or CPU utilization measurement. In some cases you have beautiful visualizations, in some cases not, but at the end of the day you are measuring wall clock. It's important obviously because it affects the user experience, and it could affect other metrics. So the longer your workload takes, the more battery you might be consuming, or the more energy you might be spending. So think about those other aspects. Obviously, this is one of those topics that Linaro is heavily involved with. We have guys who have worked on boot time improvement, for instance. We heard in the keynote from Microsoft where they're proud of how fast their system boots on a simulator, right? So these are the kind of stuff that we work with on a daily basis. Energy efficiency. So obviously, ARM coming from a more embedded and portable background, these are important, not necessarily in all kind of cases and projects. For instance, what I have been working on more recently in the cloud, this is less important because the hardware and the cloud providers take care of most of the cost savings for you. So people don't necessarily think about those, but there might be cases where even in the cloud you might want to think about this. With embedded devices and mobile and portable devices, obviously it's not just software, so again, keep that in mind. Once I was having this conversation with somebody from Apple, and he mentioned, well, the CPU works well, the software works well, but we have to improve the hardware. And that was like a long time ago, talking about LCDs, right? So every year, obviously, you're improving your software, but also component selection and choosing the right hardware and improving the hardware is very important when it comes to this metric. And quality of output, as I mentioned, imagine you have some kind of machine learning model you trained in TensorFlow, for instance, which is quite common. So if you have a team of machine learning experts, they might use TensorFlow on a desktop machine with massive NVIDIA GPUs, training models with, for instance, 32-bit floating point weights in the model. You can't necessarily take that model and run it on a mobile or an embedded system. That's where the idea of neural network processors come into play. ARM has some neural network processors. Something I've seen in the projects I was involved with was Hexagon from Qualcomm. And in those cases, what you would need to do is not just think about these two metrics, but also about what happens when you convert your models to use these co-processors. So you might be using the GPU for some of your workloads, or you might be using the specialized neural network co-processor, and in those cases the quality can drop. So if you're trying to improve efficiency or the speed by optimizing your models and using those co-processors, you might be losing quality, and depending on your application, the quality metrics are different, obviously. Using co-processors and GPUs, this is again something that Linaro engineers have experience with. Just in case you hear somebody talking about it, come to us. So those were the what to measure in most projects. Now let's look at the steps. So usually when you're going about porting code and taking care of the performance of all those different types of metrics. System performance is very important, something that we've seen even more experienced teams who are very focused on their application not think about. And we've had a few really good examples of where the engineers were focused on their own source code, on their own application, while the problems were coming from system or the system libraries or even the hardware and the firmware. I've got an example of these, which I'll cover later. Then it comes, once you've done your measurements and you know what is good, what is not so good, and what is really bad, that gives you a list of priorities, what you need to focus on during your porting project. Then it comes optimizing and fine-tuning. So again, you might use different tools, you might use different parts of the chip, whether it's the GPU or the CPU, or the newer specialized instructions that come out every year from ARM. Obviously, again, the tasks range from the more simple to the very complex. Again, we've worked on many of these types of projects. We are familiar, and I've got a couple of examples about, for instance, vectorization and measuring the system, where we found we could optimize, or in some cases, when it's the firmware or the hardware, the optimization is not possible, so you have to find workarounds. So that would be the second step in any such project. You measure, you do the optimization, and then with maintenance, obviously, this is something that's important. Again, you have to keep this in mind, because just optimizing something may not necessarily be the last step. So think about future generations of the chips coming out. For instance, if you're running your workloads in the cloud, cloud providers update their hardware and they provide better cost savings for you. So quite often you might want to compromise on today's performance to keep compatibility with those future generations of hardware. And we had cases like this where our clients were concerned that some specific measurements and some specific optimizations on the current generation of platforms don't necessarily translate to future generations. So they compromised on today's performance a little bit, just so that they are future compatible, if you like. And there are also tools and services from Linaro, for example, Linux kernel with measuring the regression with Linux kernel patches. So there are tools and services that we're providing for continuous maintenance. So those are the steps. Now let's look at the how. I'll call these the easy parts, because quite often you can parallelize these works, and the tools are really good. So if you have some C++ code that is not super performance critical, chances are you can just take the same code and recompile it for your new target. And by the way, when I talk about porting, it's not just porting from other architectures to AARCH64. You might be porting code from older generations of ARM to the newer platforms. There are, for instance, automotive companies bringing microcontroller code over to A-class processors. So those migrations are also important. You have to think about those cases. But quite often C++ code, you can either just compile out of the box. The tools are really good, LLVM and GCC, or you might just need to use a different library in your new target to get almost the same behavior as your previous platform. There are cases where people don't want to recompile. There are virtual machines for these cases, especially with legacy tools and systems. Past few months, we've had queries about, can we run X86 code on ARM? And the answer is yes, of course. And we provided a complete plan of what options are available out there. One case I worked on personally was running .NET X86 compiled binaries using Wine on a Raspberry Pi. And if you can do that, pretty much anything else is possible. So these are the easy stuff. You can get by and in many cases have multiple engineers work on the project to get your basic proof of concept running. Then there are the moderate stuff. more complex and more mature projects, they usually involve macros and bits of the code that are being selectively compiled depending on the target. So in those cases, the code might fall back to the standard generic C++, where you might get some kind of performance regression. These usually can be mitigated by either just disabling the platform-specific parts, or you might need to write handwritten vectorization code, for example, or handwritten assembly code. Vectorization doesn't necessarily mean assembly code. You could use C++ intrinsics. ARM has really good support for those. Or you could use specific libraries. So there are optimized libraries from ARM, for instance, and other partners of ARM. In case of those libraries, for instance, string operations or processing JSON data, you could look at what libraries are available already optimized, so you don't have to do that. There are people who've got projects that involve many years of code, and even before vectorization existed on ARM or on other platforms, they were doing crazy stuff. And nowadays, a lot of those handwritten code, optimized code, you can just find some libraries that do the job. So if your team is happy or your project are happy to take those libraries and replace existing code, that would be a better option than writing hand code. But this is something, again, we've been involved with. And then you have the difficult and the expensive. Examples, this is something I'm working on personally as we speak these days. Multi-socket machines are coming out in the cloud, multi-socket ARM systems. AWS is already providing those. Cache contention becomes a problem. There are many software systems out there that already use things like libnuma to optimize for these kinds of systems. And these are pretty much, they're new, right, to the ARM ecosystem. So it can take longer to translate, years and years of work, optimization work that's gone to your previous platforms, to bring them up to speed with the new platforms. And the other thing that makes these difficult, as I mentioned, is you can't necessarily just throw more engineers at it. You sometimes need the same person spending days, weeks, months just to find out what the problems are, let alone fixing the problems. Then the tools aren't great, and it's not about ARM. Generally, when it comes to some of this stuff, like measuring cache contention, for example, or measuring multi-socket performance, across the board, it's very difficult. Tools are command line based, documentation is poor, so you really need people who are super skilled at this stuff. And whenever I can, I just keep pushing for better tools. But these stuff are complex, it takes time, and when you look at the broader ecosystem, there might be fewer people who care about these, so that slows things down. So let's look at a recent project. We had a case where we were porting code from X86, mostly optimized for X86, to AARCH64 Neoverse. And we measured everything: hardware, operating system, system libraries, and application. One interesting finding was that there were TCP/IP packet processing functions that were quite slow on Graviton 3, affecting absolutely everything, especially if you have a server application. TCP/IP is pretty important. Graviton 4 addressed all of these. We couldn't do anything with 3. So this is one example. Measuring system libraries and the system tools. One example is address to line is a tool that developers are familiar with on Linux. It translates addresses to source code lines, so to make debugging easier. And this tool was super slow on Graviton 3 compared with Graviton 4 and Intel. You could easily see that it was taking 20 times longer. Something that was completed in 1 minute would take 20 minutes to complete. So these system libraries and tools, they're important. Newer libraries, they're not necessarily faster. So we had a case where one of the operating systems we were measuring on Graviton's, the MySQL libraries in the operating system in the distro were slower than the older versions. So that was affecting parts of the system. The tool chains are really important. Again, this is something that application developers might not think about, but and sometimes it gets a bit political if you have multiple teams looking at, one team looking at the tooling, another team looking at your other parts of your project. They might think, well, let's just upgrade to the next version, but keep in mind, we were talking about GCC 15 in the keynote today, right? And there are people still using GCC 10. And ARM is not investing in GCC 10 when it comes to the cloud platforms. So you really need to take care of that, because code generation makes a big difference. And then finally, the application code. For this particular case, we optimized the vectorized parts manually with SV and SV and neon code, SV2, SV and neon code. You saw some numbers on the screen in the keynotes today, improvements like 10%, 20%, 30%, compared with generic code, as well as compared with older platforms. So counting just on the next generation of hardware doesn't work. You really have to do the work. So this is an example of a step-by-step how to go from the higher level stuff down to the nitty-gritties of the code. And I guess I have 5 minutes. Just a quick look at the tools. There is LIS25. It can help you with cross-platform comparisons. In my case, for instance, you can run Forge and look at C++ or Fortran code on X86 and do the same thing on ARM. And I am not aware of many other tools that can do this, so it's a good tool to start with if you're porting code, and it would show you where the differences are. Once you know those differences, then you can move on to using ARM Streamline and performance tools. You get disassembly from ARM Streamline, you get nice visualizations, for instance, compared with Linux Perf, which is just a command line tool. And it does support a lot of stuff that you might not think about, but if your customers or your project really needs it, one example is, well, you can actually do JIT code performance analysis with ARM Streamline. It might need a bit of manual setting up at the beginning, but it works. Last but not least, Linux Perf, which is very important, and I would recommend using Linux Perf and tools like that, where those tools above are not necessarily the best. So, for instance, when it comes to collecting JIT code performance data, you cannot collect that data with those tools. Linux Perf is very, very handy. Then you can visualize it, for instance. Once you've collected the data, you can visualize it with a Streamline. There is support for the newer ARM SPE counters, of course, in Perf, which is great. If your project needs more than the kind of older generation PMU counters, you do need SPE. And in that case, you have to use bare metal systems. So again, when it comes to IT and setting up your development environment, right from the beginning, think, do you need a virtual machine, or is that not enough? Do you need a bare metal system? In many other cases I'll be working on, I did need bare metal system, because otherwise I can't get access to the SPE and cache data. So these are the tools. Just a few pictures. This is LIS25. We have a guy here from the Forge team, if anybody has any questions. Here we are showing the annotation of the workload, where the CPU is consuming, for instance, 74.4% of the CPU in this case on that line. So it's a good visualization tool. You can do this again on Intel as well as ARM. So it gives you a good comparison. ARM Performance Studio, it gives you disassembly, and a lot of counters are visualized really in a nice way. You can use that data. It does support ARM Mali as well, but of course that's a coprocessor. If your chip has other types of GPUs and coprocessors, you need vendor-specific tools. And this is Linux Perf doing a cache contention data presentation. So you can dig into the code and find out. 5 minutes. If any questions, I'm done. Okay, seems like nobody has any questions.
I have a question. Just curious, how do you collect information about hardware, software? Which tools do you use?
So when you're collecting data using ARM Streamline, there is a secondary part to the system. It's called GatorD. It's an open source tool. You compile it, you put it on the target. It does come pre-compiled as a binary within the ARM Studio, Performance Studio packages. So you just put that on the system and run in different ways. You could say, I want to measure the entire system or just a specific process, and it sends the data back to your host where you're hosting the visual part. So that's one way of doing it. Every tool is different. Obviously, with Perf, you're running the data collection using Perf tool itself on the target.
Okay, so that's great.
And it collects the different types of PMU counters from the hardware. If you really need to do lower level than that, lower level than the kernel, then you need access to the hardware and JTAG and stuff like that.
Oh, thank you.
Okay, if any questions, you can come find me after the sessions. Thank you.